Okay, welcome back Physics 20s to our next lesson. This is 3.1 and today we're going to be talking about force. Okay, so this whole next unit is going to be focused on forces, and forces are measured in newtons. Where this word comes from is the name of a person, Isaac Newton. Isaac Newton had a whole bunch of contributions to science. He invented calculus, which is pretty crazy. He studied optics and light. You look at that more a little bit in Physics 30. And he studied the forces that exist here on Earth and out in space. And that's what we're going to be looking at, the forces here on Earth in Chapter 3 and the forces out in space in Chapter 4. So what is force? Since it's going to be the main topic of our discussion, a force is a push or a pull. So say we have a mass, if someone is going to be pushing on it or pulling on it, they're going to be applying a force. And a force causes acceleration. We looked at accelerated motion in the first unit. Now we're going to be looking at causing that acceleration. So if there's a net force, it's going to be speeding up or slowing down. This is a vector, so the direction that you push or pull something will affect the direction that it's going to move, and it is measured in newtons, as we mentioned the relation to Isaac Newton. And we're going to be looking at Newton's laws of motion. And his first law says that an object will remain at a constant velocity in a straight line when there is no net force. The first law is talking about no force or no net force. And I want to highlight or focus on this word net force. That means the overall force. Doesn't necessarily mean that there's no forces present, but it means that overall they're all balanced out. There's no overall force. So for example, if we had these two people applying a force to this box, if we have a force in this direction that is 10 newtons and a force in this direction that is also 10 newtons, then there would be a net force of 20 newtons in that direction. But if one person, let's say this person over here, then starts pulling in this direction, then because it's a vector, they'd be pulling at negative 10. So then we have 10 and negative 10, and this is going to cancel out to an F net equals positive 10 plus negative 10, both of those forces, and it's going to equal 0. In this case, it's not going to accelerate because the forces are balanced. Let's look at some other places that this would apply. So let's go out into space, and let's have some masses. If we have a mass and it is moving at 5 meters per second out of space, it's not close to any other objects, so there's no forces acting on it, it should continue to move at 5 meters per second. It will stay at a constant velocity and move in a straight line if there's no forces. Also, if something stopped and it is at rest, that's a constant velocity of 0 meters per second. It should just stay at rest. It's not going to move at all if there's no forces here in space. So I guess what that means is if you are stopped out in space, you don't really have any way to get moving unless you have something that can apply a force to you. Otherwise, you are stuck there. But also that if you are moving at a constant velocity, so say you're trying to get to Mars and you're going at something like 1,000 kilometers per hour, you could just turn off the jets because you're just going to keep going. There's not going to be slowing down due to friction or air resistance. There's no forces out there. So you should just keep going at that constant velocity if there's no forces. Next, let's consider that if we're on Earth and we have this person, or a very large person here compared to the Earth, and they're holding a mass. And let's say they're holding it stationary, it's not accelerating. Well, this means that the overall net force is 0, but again, there could be forces going on here. And if you're close to a mass, there's a force of gravity. We'll talk about this a lot in Chapter 4, but a force of gravity pulling this object down. Now I'm going to call down here negative because we need to keep a track of signs. So I'm going to put negative 10. Hopefully you can see that newtons, but this isn't accelerating. We said they're holding it there stationary. And if it's not accelerating, the net force must be 0. So then there must be a force that is going upwards that is making this cancel out of 10 newtons. So that must be what the person is pushing up with. Force of gravity down 10, lifting up with a force of 10, and it doesn't accelerate. Okay, so next let's look at some applications of Newton's first law. I'm going to use the example of a car crash. So let's say here you are in your convertible and you're sitting here at a stoplight when another car comes in and collides with the rear vehicle. So here we're going to apply the concept that masses want to stay at that constant velocity. If they're moving at a velocity, they want to stay there. If they're at rest, they want to stay at rest. So I'm going to focus on the red car first, that he was at rest. So there's a force applied to his body, but if his head, there's nothing pushing on it, his head wants to stay at rest. So even though the red car gets moved forward, his head wants to stay at rest. And he ends up looking like this. And this is called whiplash, where your head goes flying back. There's actually nothing pushing your head back. It's just something pushes your body forward and your head stays back there because it wants to stay at the velocity of 0. So I can say here that an object at rest wants to stay at rest or stay at that constant velocity because there's no force acting on that person's head. Now we're going to look at the purple car and say that this person was traveling with a pretty high, probably initial velocity, and their body is going to want to stay at that constant velocity. So if there's no seatbelt to apply a force to them, their body's going to continue moving at that constant velocity. So they have the collision and they're going to be flying forwards at the same speed that they were when the collision happened. So with these cartoons here, it may seem kind of light and comical, but this can have some very significant effects in real car crashes. So good information to take into a vehicle. And I could sum this up in an object in motion stays in motion. Again, unless there is a force applied to it. So hopefully you have a seatbelt applying that force to slow you down and a headrest applying a force to save your neck. But Newton's first law was looking at when there's no net force applied. Now, how much a moving mass is going to stay moving and a stopped mass is going to stay stopped relates to the word called inertia. So this is from Newton's first law, and it's basically the tendency to do those things, the tendency for an object to remain at its initial velocity. How much force is it going to take to change its initial velocity? And this is dependent on mass. And I kind of saw this example when I just put my garbage out on the street, that if I put a heavy waste container there compared to some light cardboard that was going to be recycled, I was kind of concerned about how these would move in the wind. So if the wind applies a force to both of these, the garbage can is a pretty big mass, but the cardboard is pretty small. So both of these are at a constant velocity of 0, and again, they're going to have a tendency to stay there. But which one is harder to change? That is the one with the more mass. The garbage can has more inertia, so it's going to stay there or want to stay there more than the cardboard. And this can also be written as F is equal to ma. A force is going to cause a mass to accelerate. Now, if you increase the mass, you're going to have to increase the force to have the same acceleration. But if you have a small mass, you don't need very much force to cause it to accelerate. So the wind comes and blows here, and the garbage can might shake a little bit, but the cardboard could fly away. So inertia, the tendency to stay at a constant velocity, is Newton's first law. This formula right here, F is equal to ma, is Newton's second law. And this is saying when the net force is not 0. So you can see this is F net is equal to ma. If F net was 0, a mass wouldn't accelerate. There'd be no acceleration. But if we do have a number here, there's an overall net force, how much something is going to accelerate is based off of its mass. So let's just do some quick examples with this. Let's say someone's applying 54 newtons to a 20 kilogram box. What's the acceleration? I would go F net is equal to mass times acceleration. I'm asked for acceleration, so I'll divide by mass on both sides. And I'll just take F net of 54, because that's the only force I see, newtons, divided by the mass of 20 kilograms. And I get an acceleration of 2.7 meters per second squared. That's how fast it's going to be speeding up. So important to note, that's not its velocity, that's its acceleration. So it's going to keep speeding up, speeding up, speeding up if you keep applying that force. Now in real life, there will be quite a bit of friction probably on this box, but we'll look at handling multiple forces in the next lesson. And just one more example here. It says, what is the force of gravity acting on this mass? So we have an 8 kilogram mass that is falling due to the force of gravity. So this is accelerating. What is the force? So I would set up F net is equal to ma. In this case, we're focusing on the force of gravity. That is the F net, because we're not going to talk about any other forces of air resistance at this point. So Fg is causing a mass to accelerate. What is that force of gravity? Well, I know the mass is 8.0 kilograms. Now I need to know the acceleration, which we do know that on Earth, things will be accelerating at 9.81. So times by 9.81 meters per second squared, and I get the force to be 78.48 newtons. If I only had 2 digits, I would just round this to 78 newtons as the gravitational force. Okay, so I hope that video made sense and you have a better understanding of Newton's first and second law and how to apply them to questions. Thank you for watching this video, and I will see you in the next lesson.